Institute of Complex Systems. And my supervisors are Tobias Gala and Raúl Toral. I am a first-year PhD student. So today I'm going to talk a little bit about a phenomenon which is called anticipated synchronization. And I want to extend this kind of synchronization to systems with distributed delay. But first of all, let me talk a little bit about what anticipated synchronization is. So of course, it is a type of synchronization. So we have sort of two systems that are synchronized, but they are not in the same state. So one system is running ahead of the other. So for instance, in this animation that you can see here, you can see that one system is ahead of the other one. So the maximum in the orange line occurs earlier than the maximum in the blue line. And how can we get that? Well, there are several configurations in which we can use in order to get this sort of anticipated synchronization. But for simplicity, we are going to use the following one, which is just one dynamical system, which we will call driver. And then we will create an exact copy, same parameters, same everything. And this copy, we're going to call it driven system. And we will do the same modifications to the dynamics. The dynamics of the driver are going to be unchanged, so we are not modifying that, but we are modifying the dynamics of the driven system. In particular, we are coupling it to the current state of the driver, and we are also coupling it to itself, but with some given delay. So the equations of this sort of system will be given by something like this, where f, it can be whatever. Like it can be a simple linear system, and it will work, but you can also put there an excitable system, or you can also put, for instance, a chaotic system. So this example over here is for a Rosler system, so a chaotic system. And this is very well known, and it has been studied since the early 2000s. So this is already very well studied. Also, it has been studied for a spatially extended system, for some configurations in which we don't have these two copies in neuronal system, and so on. But now, I was interested in studying it for distributed delay. So, for instance, one simple thing that we can do is, okay, what happens if I put a second delay line? So now we have two different delay lines with different delays, and maybe even with different weights. So now the equations will look something like this. Okay, we can do 2, we can do 3, we can do 4, and we can also do infinite of them. So we can do a distributed delay. So we just grab a distribution of our delays, and we just plugged it in, and we have this sort of system. And this, like, we got motivation to do this because maybe you have some uncertainty in your delay. So this will model an uncertainty on the delay that can come from practical ideas or just from the theory. And also, it will be like a first approach to get that the time delay is also a stochastic variable. So we have sort of different motivations to study this sort of system. And now let's see, well, also I should mention that from now on, when I talk about distributed delay, I will just use a uniformly distributed delay. But it's just a matter of those, so you don't get lost. Okay, so here we have the results for a single delay. So you can see that the two systems are identical and they are just shifted by some time. But now, let me put some uniformly distributed delay. And as you can see, again, the two systems are shifted by some time, so there is anticipated synchronization. But also, in some cases, the systems are not identical, and we can find some sort of amplification. And this is interesting for us because one application will be to remove unwanted spikes using this as a forecaster. And since there is an amplification, we are able to detect the spike even earlier. So this was a kind of interesting thing. But we want to get some theoretical insights. So in order to get some theoretical insight, let me move to a linear system. So let me write here a damped harmonic oscillator, which, of course, in this case, you will take, but David, I can solve this. I can write the solution for this. Like, why are you telling me that you want to study the anticipated synchronization in this thing if I am already able to write the solution? And I mean, you are right. I can write the solution. But the good thing is that we can get some theoretical insight of the problem by studying this simple linear case. And also, I mean, as most of you, I am a physicist, so we all love the harmonic oscillator, and we tend to use it quite a lot. So let me just use the harmonic oscillator for a little bit. Okay, so now I will do the configuration that we have already explained. I will create a second copy of the system, same parameters, same everything, and I will add the coupling. So I will add some coupling here. In general, I will put a general distribution just to keep it as general as possible. And we will try to see how the solution looks like in this case. So how do we find the solution? Same idea as before. We say, okay, let's assume that this coupling terms are 0. Let me assume that for a little bit. And from here, I will save you the math, but trust me that from here, you can arrive to this result. So here you can see that there is some amplification, some constant that we can compute. And then there is also some anticipation, but now the anticipation time is this sort of funny average over the distribution. So this is nice because we have a solution which exhibits anticipated synchronization and also has some amplification. The second question is, okay, this is a solution, but is this the stable solution? Is this what we observe if we plug in some simulations? So again, since we are in a linear system, we can do some theory. So we can study the stability of these variables over here from a theoretical point of view. And as always, even for chaotic systems, we can do some simulations. So what are we plotting here? Here in the colors, what I am plotting is the maximum of the cross correlation function between the driver and the driven. So if it's close to 1, it means that the driver and the driven looks similar. And if it's not 1, it means that something is going on and we don't have synchronization. So we sort of see 3 regions over here. There is one wide region in which, of course, the maximum of the cross correlation function is close to 1. So there is synchronization. And as you can see here, if we plot a trajectory, we can see that there is indeed some anticipated synchronization. And we can also get that from the theory, which is this dashed line over here separating this region from the next one. Then we have this second region in which there is not synchronization, but still the two systems are going to 0. And last but not least, we have this last region in which I am putting it in red because what is really happening is that the driven system is diverging. So of course, we cannot compute the cross correlation because one system is going to infinity. So this is nice, but let me move back to the real world because the linear oscillator is great, but we need to have some real systems going on also. So let me study again some chaotic system. This one I have already used it, is the Rosler system. But here I am using just 2 equally weighted delays. And as you can see here, there is, in this variable in particular, there is some sort of amplification. And in this variable, sometimes there is an amplification, sometimes there isn't, and this thing also evolves with time. So this is kind of complicated. I have some sort of intuition about this also from a more complicated linear system. But this, of course, also has nonlinear effects, so it's not easy at all. And just as another example, we can also do this for the Lorentz system, which is also a very popular model for chaos. I guess that most of you are familiar with this model. And as you can see here, there is also anticipated synchronization, but sometimes the two trajectories are not exactly the same. And last but not least, let me finish with excitable system, because I have already told you that this also can happen for excitable systems. And, well, I guess that most of you are already familiar with what an excitable system is, but just as a brief review, an excitable system is a system in which we have one fixed point, but we have sort of 2 different ways, or maybe even more, to arrive to this fixed point. So for instance, here, if you're in the vicinity of this fixed point, you will just do a small arc and get stuck there in the deterministic model. But if you are over here, you will do a complete revolution in order to arrive to the fixed point. So a deterministic excitable model, if it's just a single system, is not so interesting. But what we can do is to plug some noise. So then what we have is that the system will oscillate around the fixed point, but then maybe at some point it will arrive here, and then it will start doing a full revolution until it gets again to this fixed point, and then it will oscillate and have another oscillation, and so on and so forth. So this anticipated synchronization does also happen for excitable system with distributed delay. Let's see. So as you can see here, this is a Fishkin-Nagumo, so a model for neurons, a very famous excitable model for neurons. And as you can see here, you can also get anticipated synchronization when you have some spikes. And the results for a single and for two or a uniformly distributed delay are also quite similar in this case. So that's basically all that I want to mention. So just to sum up, we can find anticipated synchronization in systems with distributed delay. This is, we can see it in linear systems and in chaotic and excitable systems. We can also, in some cases, get an amplification of the signal, which is quite nice for me, as I have already mentioned. And then, even though this problem is too hard to approach it in a chaotic configuration, using a chaotic system or an excitable system, we can get some nice results and some sort of intuition using a nice linear system. And that's all that I want to mention. So thank you very much for your attention, and thanks to all the organizers.
Thank you. Thanks, David. Questions? Comments? I have a question. So what's the key difference between a single delay and these multiple delays that you use? For instance, amplification, you only get when you have distributed delays? Or?
Yes, well, it's not this one. Let me go back even more. So when you have a single delay, the signal are just shifted. Mm-hmm. So they are exactly the same, but they are shifted by some time. But when you have distributed delay, now, first of all, the shifting is not even constant,
okay.
And it's also not exactly the average delay, it's something a little bit different. And also, there is some amplification, which is also not constant in the more general case, and it can also look quite different from variable to variable. Indeed, in some systems, we do find this amplification, but in some other systems, we do not find this sort of amplification.
Okay, thank you.
So maybe following up on Marcus' question, so you said that most of the times when you talk about distributed delays, it's a uniform distribution. So if you take your uniformly distributed delays and starts making smaller and smaller and smaller the variance, do you see continuous changes in all these properties of the anticipated synchronization, or is something that appears?
No, yes, if you take, for instance, a uniformly distributed delay and you start to shrink the width of the distribution, what you will see is that you start to get closer and closer to the single delay case, and when the distribution is almost just a single point, you recover the single delay case.
It's a continuous change of behavior. Okay.
It's a continuous change, exactly.
Thank you.
Okay, so let's thank David again. Thank you, David. Now we have the last talk of this session, which is